In this video, we will be discussing binary search trees. But before we commence, it is imperative that we must be attuned to some of the pertinent terminologies to be used. First are the children or child nodes, which refers to the nodes that can be found cascading from a single node, which is their parent's node. An example is provided to make the definition easier to follow. Next are the root nodes. These are the nodes that you don't have a parent node, and it is the beginning of any tree data structures. Root nodes are invariably at the uppermost level or level zero of any tree data structure. And last, the last relevant terminology is leaf. These simply are the nodes which have no children.
After learning about the important terminology, we can now define what a binary search tree is. A binary search tree is a type of binary tree whose structure is designed for efficient searching of nodes and also for a quick alteration and modification of a collection of data. This is because a binary search tree is an ordered tree data structure that is predicated on the architecture of a basic binary search algorithm. In a binary search tree, the nodes that have a smaller or lesser value are placed in the left subtree, and those that have greater values are put into the right subtree. Here is an example wherein the root node is 15 and parent node 13 is placed on its left because it has a value smaller than 15, while node 19 is put on the right as its value is larger than the root node's value. If we look at the whole tree, we can see that the leaf node 11 is on the left side on its parent node 13 because it has a smaller value. The same is the case for the leaf node 12, which is also on the left side because it has a smaller value than its parent node 19. But since leaf node 21 is greater than its parent, node 19, it is placed on its right.
To better understand what a binary search tree is, we are going to use a larger example. This time, our root node will be valued at 11. This node will have two subtrees. The node 7 will be the parent of left subtrees because it has a lesser value, while node 13 will be the parent for right subtrees as it has a value greater than the root node. Starting with left subtrees, the node on the left should not be greater than the parent node, which is 7. This is because any value that is greater than its parent node should be placed on the right. Hence why node 9 is found on the right side of node 7. The same principle applies on child nodes of node 9, with node 8 placed on its left and node 10 on its right. However, it should be noted that albeit node 10 can be greater than its parent node, it should not be greater than the root node at level 0, because it is part of the left subtree, which means all values must be smaller than the value of the root node. Lastly, the right subtree is the antithesis for the left subtree, with all of its nodes having a value larger than the root node.
Binary search trees are an optimum solution to any real-world problems because it aims to solve this problem with speed and accuracy. And since it is contrived into branches in a tree, this enables the algorithm to quickly locate the elements in a tree data structure. Therefore, the elements of key value comparisons that the program has to make will decrease, which then leads to a more efficient searching. By arranging the elements in a way wherein smaller values are placed on the left and higher values on the right, it helps the algorithm to know on which sides to look for whenever it is looking for an element. If it's searching for an element whose value is greater than its parent node, then it can just disregard the left side and search for its exclusively on the right side. Dito, but this time if it is all seeking for something that has smaller value compared to its parent's node, then it will do so on the left side of the tree data structure.
Here is an example of how the search operation happens in a binary search tree. In this example, the algorithm is tasked to search for the number 10, and because its value is lesser than the root node, which is 12, therefore the algorithm can then disregard the right subtree in order to save them locating for the element. The parent node on the left subtree is then compared with the element the algorithm is seeking. And because it is greater than the parent node, which is 7, this means the element it is looking for must be on the right. At this moment, we are on the node 9, and since it is smaller than 10, this means that the element ought to be found on its right side. Now the value matches and the element is successfully found. The value is then returned, thereby completing the process.
For the next example is an insert operation. The values that need to be inserted are 12, 7, 9, 19, 5, and 10. This is very straightforward and the first to be inserted is 12, which makes it with root node. The succeeding value is 7 and it must be compared with the root node. 7 is smaller than 12 and it must be placed on the left. The next element is 9, and because it is greater than its parent node, which is 7, therefore, it should be placed on its right. With 3 elements placed, we must compare the remaining elements with the root node and identify their place. Starting with 19, it is placed on the right subtree because it is greater than root node. In case of element 5, it is smaller than both node 12 and node 7, hence why it is placed on the left as a child node of 7. Lastly, 10 is less than 12, which means that it must be placed on the left subtree. However, it is greater than both 7 and 9, which is why it must be placed on the right as the child node of 9.
The delete operation in a binary search tree is the most intricate among the three operations, especially because it has different scenarios. Deleting a leaf can be relatively easy, but deleting a root node requires a shift wherein one of the remaining elements should be promoted as the new root node. The first example is the easiest. Deleting a leaf simply requires removing the leaf that needs to be deleted. For example, we just removed the leaf 19 and the process is now completed. The next example will show what will happen if a parent node with one child is reducted. This is also fairly easy because the deleted node is simply replaced by its child node and the process is completed.
The third case in a delete operation is divided into two categories, which are the in-order predecessor and the in-order successor. Starting with the in-order predecessor, when the root node 12 is deleted, it must be replaced with the largest value found in the left subtree. In this case, leaf 10 has the largest value and it will now be the root node once 12 is deleted. In the case of in-order successor, the root node is to be replaced with the largest value found in the right subtree. Therefore, once the root node 12 is deleted, it will be replaced by leaf 19. And this is where our discussion ends. Thank you and goodbye.